becomes more complicated. For our talk, visualizing the stability of 2D point sets from dimensionality reduction techniques. Visualizing and analyzing a single 2D point set is rather straightforward. One can map points directly to their 2D position in screen space. However, visualization becomes more complicated if point positions adhere to a random process. By sampling from this process, we can obtain an ensemble of 2D point sets, so-called arrangements. Here we can see 8 of such sets. Most importantly, we have a one-to-one correspondence of points between each pair of scatter plots. We can think of this kind of data arising in the context of crowd analysis, simulations of moving objects such as SPH and fluid dynamics, or non-deterministic dimensionality reduction techniques. For instance, when projecting n high-dimensional points of the 2D plane, the commonly used dimensionality reduction technique TS&E outputs a different arrangement of 2D points for each run. Finding and highlighting stable regions of points is the main focus of our work. By stable regions, we mean subgroups of points that are located close by in all, or at least most of the arrangements of our ensemble. In practice, this information facilitates distinguishing coincidental patterns from frequent ones, so that we can actually put confidence in the correct patterns. Rush and link implementations already allow us to verify the stability of individual regions. Here we can see that the highlighted points appear jointly in all arrangements. However, in order to grasp the larger picture, that all arrangements are similar up to a rotation, we would have to check notably more than one point subgroup. Obviously, this approach neither does scale for larger point sets, nor is suitable for large ensemble sizes. We propose to render a static visualization in the background of a point set that exposes stability of regions in one glance. It is computed in 3 steps. Given a point set chosen from the ensemble, we first compute a higher order Voronoi diagram. This diagram defines the subgroups of points we are going to investigate. In the second step, we compute a stability value for each subgroup and color each cell of the Voronoi diagram accordingly. In the last step, we use the graph topology of the Voronoi diagram to merge small subgroups of stable points to larger subgroups that we then visualize by drawing separating ridges. Here you can see the colored Voronoi diagram, as well as our visualization for an ensemble of 100 point sets with roughly 11,000 points each. We now discuss the first step, the selection of subgroups of points to investigate. Here, we only consider subgroups of a fixed cardinality k, where k is a hyperparameter that controls the locality of our method. There are 3 possible options that we can think of. First, we can investigate all n over k many subgroups. However, even for small values of k, this approach does not scale well with respect to the amount of points n. To reduce the number of subgroups, we can decide to restrict ourselves to one subgroup per point. We simply take a point itself together with its k-1 nearest neighbors as a single subgroup. Unfortunately, this approach has another flaw. Consider the arrangement depicted on the right with k equals 3. When viewing the 2 neighborhoods of the points on the left, we see that the disks centered at each point and containing the 2 nearest neighbors actually never do contain one of the 5 points on the right. The same observation can be made for the right 5 points. Hence, no investigated subgroup contains points from the left, respectively right, simultaneously. Both groups are thus disconnected. For our analysis, this means that we cannot assess if the left points move independently of the right points when paging through the ensemble, or if both groups actually move jointly and thus form a conflated, stable region. Ideally, we should also consider the 3 nearest neighbors of the location marked by the blue cross. By computing the 3-order Voronoi diagram, we obtain all 3 neighborhoods for any location in the 2D plane. Hereby, Each cell corresponds to a single neighborhood, and neighborhoods of adjacent cells only disagree by 1 point. Hence, the Voronoi diagram gives rise to a relation on the investigated subgroups that forms a connected graph. This structure will become useful later on when fusing subgroups. In comparison, the k-1 neighbors approach misses out on all neighborhoods whose cells do not contain a point, as is barely the case for the orange cell. Its neighborhood is given by the 3 nearest neighbors of the blue cross. Note that k-order Voronoi diagrams of n points develop at most big O of k times n cells. Next, we describe how to compute a stability measure for each selected subgroup. On the left, we can see the Voronoi diagram describing the subgroups we intend to analyze, and on the right we can see the various arrangements in the ensemble. For demonstration purposes, we focus only on a single Voronoi cell highlighted in orange. The points in its corresponding 3 neighborhood are highlighted as well. To compute the stability, we search for the corresponding 3 points in each arrangement and place a disk with radius as small as possible such that all 3 points are contained. Then, for each disk, we count the amount of contained points and divide the value of k by the obtained number. The resulting stability values are shown in blue boxes. They become maximal, that is 1, if a disk contains no additional points except for the highlighted ones, and approaches 0 as more points enter the disk. By aggregating all values, we obtain an overall stability value of the Voronoi cell with respect to the whole ensemble. This number then is mapped to the color channel of the Voronoi diagram. Repeating this process for all cells yields a colored Voronoi diagram where we can already dissect the stable regions quite well. However, especially for large point sets, colored Voronoi diagrams become highly fragmented and difficult to read. We propose a clustering technique based on hierarchical density-based clustering in order to discern a clean-up version of our visualization. By iterating all Voronoi cells in descending order according to their stability, we build a hierarchical representation where 2 subtrees of cells are merged as soon as they become connected. Here you can see the process. Note how long it takes to merge the top left and bottom right cells. Both regions are separated by a band of highly unstable cells, which results in 2 dominant subtrees in the hierarchical representation. After making the representation robust to noise by fusing small subtrees, we are able to extract clusters of points that form stable subgroups. These groups are separated by ridges and thus can be perceived in our final visualization. Color hereby indicates the stability of either identified subgroups or ridges separating them. In this case, the clustering algorithm determines 2 clusters. For more details about the clustering approach, please refer to the published paper. We now present some results of our technique. In our first example, we animate 20 randomly placed 2D points by applying 4 different transformations. The first transformation rotates all points equally around the center of the bounding box. Additionally, the points are split into 2 equally sized groups, where each group is rotated either clockwise or counterclockwise around its respective center of mass. Finally, we also apply some amount of jittering to each point. We sample 20 arrangements from this animation to build our ensemble. Here we show 3 exemplary ensemble members. By running our analysis, we identify the groups of points that are rotated differently. In particular, note that the highlighted orange point is correctly counted to the bottom right set of points sharing the same counterclockwise rotation. Without our visualization, one would probably assign this point to the top left cluster. In our next example, we sample 1000 points from 8 multivariate 3D Gaussian distributions with varying centers. Then we apply 100 runs of T&E to project the points into the 2D plane. Again, we show 3 randomly chosen projections. By running our analysis, we observe well-known properties of T&E projections. Highly stable regions around each Gaussian confirm that T&E succeeds to preserve local neighborhoods consistently in all runs. However, dark blue and thus unstable ridges indicate that the positioning of the clusters with respect to each other is at random. T&E does not preserve global structure. Our final dataset covers data from a real-world scenario. Mellman et al. Performed multi-parameter cloud simulations to obtain a 3D field of 12-dimensional attribute vectors describing the amount of rain, ice, gravel, and other properties at each spatial location of a cloud. We sampled roughly 11,000 non-zero attribute vectors from a regular grid and projected them to the 2D plane by running T&E 100 times. Here we can see 3 of 100 projections. To distinguish meaningful from misleading proximity, we run our analysis and show the resulting visualization. Note that in each projection there exists a crowded area of stripes that originate from a start point. When inspecting such an area closely, we observe that the stripes themselves are stable regions. However, the relative position to each other cannot be deduced from a single projection. We assume that this star and stripes structure exists in the high-dimensional data, but it cannot accurately be presented in 2D space due to overcrowding issues. The second area we pick out shows how a single projection may convey topological structure that in fact may not exist. Here, we see a crescent moon with a small attachment. Our visualization suggests that the attachment actually is not part of the moon and additionally is split into 2 parts by a ridge of medium stability. When tracking this configuration by paging through our ensemble, we can observe that the attachment is slightly dislocated in most projections and also splits into 2 parts once in a while. This example concludes our talk. We thank you for your attention and the marvelous conference team mastering this exceptional situation. Stay healthy and hopefully we hear from each other in the following Q&A session.
Hello everyone. Thank you, Christian, for the very nice talk. So my introduction was cut a little bit due to a technical problem, but yeah, I wanted to introduce our first speaker, Christian Reinhold, on the visualizing the stability of 2D point sets from dimensional reduction techniques. And Christian is from Technical University of Munich, and he's now getting lots of claps from the YouTube channel, Christian. So it's great. So I'll encourage everyone to post your questions either on the Discord channel or the YouTube channel. So we have some good time for discussion. So I get the I get the first. Distracted by Alex's message. This is super nice. So I start with one question from the Discord channel from Rafael Martins. So his question is, are there any guidelines or advice on how many projections one should run, let's say for the same data set, before we can trust the data, trust the results of the proposed technique, and then I think his question is also trust the stability of the produced maps?
Oh, I think this highly depends on the dataset. If you have a very high dataset with very high variance, you probably want to sample much more. We just took a fixed sampling amount of 100 projections in our case, which is kind of arbitrary in our dataset. But we observed, at least for our examples, that most of the projections were rather similar, so we suppose 100 projections were fine, except for one study with multidimensional scaling, that was only in the paper where we observed that the dataset actually splits into 2 different kinds of projections. Then of course you should at least sample enough to see the split to 2 different groups. But I think this really highly depends on the dataset.
Mm-hmm. And maybe just a follow-up from, I think what the point about dataset is interesting, and then we have some survey coming up after your talk that looks exactly different dataset types. Maybe that's something to look out for in this session. But just to sort of continue on that question, Rafael also asked, and so if you assume that you run these ensembles and look for some stability or some consistent groups, would you be able to sort of interpret what these groups mean? Is there any way of explaining what the groups are?
When you want to explain, you probably could add more information to this visualization, except for only the point representation. You could also insert images. For instance, we also have a situation in the paper where we swap out the point visualization and plot numbers instead. So we just apply TSNE to the MNIST data set of numbers. And there you can also see that we identified two groups of twos, so handwritten twos. And these two groups actually were differentiated between twos that were just written with a curl on the bottom left side and a straight line just going back again. And then, of course, you can also make more sense from these groups.
Mm-hmm. You mean by referring to the actual raw data? And
exactly. For us, these are just points as by now.
Mm-hmm. Okay. I'll just look if there are some comments on the YouTube channel. One I see from Lars Linson. So he's asking, did you consider applying TSNE to subsets only to see whether they stay as clusters?
No, we did not, but I think that's a very interesting idea. So you can actually take one of these clusters that we extract from our analysis and just run TSNE on a subset. We did not do this. We can probably actually do this in order to implement something like a dive into the dataset approach. So you can see as overview or projection and then select the different clusters and get new projections for that. That would be possible, yes.
Yeah. And like Martin Skrotsky on the YouTube channel has sort of, I think it's a question, but also maybe a recommendation for future work as well. Like, can you use your technique to analyze the effect of like perplexity parameter on TSNE?
We actually have done that. Unfortunately, to be honest, perplexity, at least in our data sets, has not a very high difference in order stability. You see very low perplexity values are very bad, very high stability values, perplexity values are bad as well. But in the middle, you have a rather broad range where you can actually take perplexity values without really high modification. So we actually dropped that part out of the paper. But we thought about that as well.
Okay, you can include that in the next paper. Looks like it's getting interest. Great. So we have a question from Alexander Telea. First, he's a super nice, and then he talks about the ridges that you create in the final representation. His comment is those ridges actually resemble very much skeletons, the medial axis of the projection drawing. So the ridges tell us where we have a wrong projection because of the like as you showed in your example. I think that's the point he makes. And then he says, but the aim of the user is to have a stable projection. Can we use the info you compute to construct a stable projection, or is this out of scope?
As for now, it is out of scope. I think an idea would be this subset dive-in where you can at least say, okay, we are locally stable. We can try to run TSNE on these subsets. For a globally stable approach, you probably want to have a TSNE algorithm that is some kind of stable by itself. I mean, TSNE is random, and this is just what we want to show, but we cannot resolve this issue of randomness. This also depends on the data set. If you say, okay, we don't project from TSNE, but we just have two-dimensional point sets from, I don't know, real-world data, like crowd analysis, then you cannot influence this data set anymore. It's just as given. And then you don't have projections even more. Projections are just our use case where we applied our technique.
Okay, yeah. Then I'm sort of monitoring the channels if there are any other. So I have one question. So I think you presented as an intermediate representation. And by the way, Alex says thank you. In your when you're creating that final borderline visualization, you have this transition where you go through a hierarchical representation.
Exactly.
I thought that was quite also informative, how that hierarchical structure is constructed out of that the projection that you produce. Have you considered doing visualizations with that, or using that information to reflect some of it on your final representation, apart from the sort of the ridges that you draw?
You mean that you could also present the hierarchical representation as in the video? Actually, no, we have not thought of that, but these are obviously things where you start thinking about that when I was actually producing the video, when I was thinking, oh, it's really interesting to see this approach, and then you can also see not only in a single view how stable these different kinds of clusters are, where you can also map a size of these blocks in the hierarchical representation to some kind of significance. All the details are on the paper, and it's basically modification of hierarchical DB scan. And yeah, it would probably be a good idea to attach that on, I don't know, in a kind of dashboard.
Yeah, or some way of reflecting some of that quality on the map, or sort of enhancing those representations. I think that there is also potential to use that information.
Right, thank you very much.
It's great. Yes, I'm sort of just like monitoring. I think that's all we have for now. Thanks to the audience for all the questions, and thanks, Christian, again for your very interesting talk and for your responses. Thank you.
Thank you as well.
So we can now switch to the next talk in this session. So the next one we have is called Towards a Quantitative Survey of Dimension Reduction Techniques. It's from Mateusz Espadato, Rafael Martins, Andres Keren, Nina Hirata, and Alex Telea. It's a very interesting sort of survey with lots of interesting results, and it will be presented by Mateusz Espadato from University of Sao Paulo and University of Groningen. See you after the talk.
Hello and welcome. My name is Mateusz Espadoto. I am a PhD student at the University of São Paulo and at the University of Groningen. I'm going to present to you this paper called Towards a Quantitative Survey of Dimension Reduction Techniques. Let's get to it. So, multidimensional projections 101. Those are important tools in the data science toolset for visualization and simplification of high-dimensional data. They enable visual exploration, making possible the detection of clusters and outliers and other patterns in the data, for example. Okay, you all knew that, of course. The challenges. Well, there are really many techniques available, like dozens of techniques. So it's pretty hard to pick the best one for each case, for each data set, and how to quantify best in this case. You have a lot of surveys, which are great in terms of cataloging all the techniques, but often lack actionable results. And we have DR benchmarks, which usually are small in scope, only a few data sets and a few techniques, well, until now. So we set out to create a truly comprehensive benchmark for DR techniques. For that, we need techniques, we need data sets, we need metrics, we need an evaluation pipeline, which you can see here on the right. Well, that's easy to do, right? Well, not quite. So, collecting techniques. We needed to search the literature to find techniques. Then we needed to find usable implementations for those techniques, to integrate them into our evaluation framework, to determine important hyperparameters for each technique, to create a parameter grid, then to test everything to make sure it works. We ended up with 44 selected techniques, with some household names like PCA, MDS, LLE, ISOMAP, TSNE, UMAP, and others, and some lesser known ones. The idea was to be comprehensive, so we wanted to have techniques of many types: linear, nonlinear, global, local, manifold learners, big embedders, and so on. Then we needed to collect data sets. So we wanted to determine the important data set traits or characteristics. Then we needed to write code to compute those traits. And we pick many data sets, compute those traits, and select the data sets that sample well this trait space. Then we process the data to be compatible with the benchmark framework. We ended up with 18 real-world data sets, some popular ones like Fashionista, IMDb, SVHN, and many others according to the following traits. The type of data, which could be tabular, image, or text, dimensionality, varying from tens to low thousands, intrinsic dimensionality, which is very important, from low to high, and sparsity, also from low to high. Collecting metrics. We started selecting the air quality metrics from the literature. We tried to find the implementations, then we failed miserably because most of them were not implemented in anywhere that was easily reachable. So we implemented all metrics from scratch and integrated them into our evaluation framework. We ended up with 7 metrics in total of 3 different types. So we have scalar metrics, like trustworthiness, continuity, normalized stress, neighborhood hit, which all are pretty popular in the DR literature. Then we use the Shepherd diagram, which is a point parametric. Then we use local metrics, which measure errors per point, as average local error and stretching and compression. So, it's a summary of the ingredients. We have techniques, we have data sets, we have metrics, we have a pipeline. Okay, now it's just a matter of running the whole thing. Easy, right? Well, not quite. So, by having 44 techniques over 18 data sets, using grid search to explore combinations of values for hyperparameters, we ended up with more than 5,000 unique runs. And we had to compute the metrics for every single run. For that, we needed 8 servers with 16 cores and 256 gigabytes of RAM each, which is quite something. So, grid search gives us measurements for every run of each technique for each dataset with each set of parameters. Having all this data, we decided to group results into 2 views. So, we have what we call a dataset-wise view, where we pick the best projection overall for each data set. By doing this, we try to answer the following question. How good is technique T when you tuned for a single data set? Okay, then we have a projection-wise view, where we fix a preset configuration, and we try to answer the question, how good is technique T when using a preset configuration for all data sets? In this case, since we did not have the preset configuration before running the benchmark, we used the configuration that yielded the best results most of the time as a preset, which we believe was fair enough. So, for the dataset-wise view, we have this huge heat map, which unfortunately is not big enough so we can read the results. It takes a full page of the paper. But it's important to be here so we can see the color patterns, which you will understand in a moment. So, in this heat map, we have the aggregated quality, which is the average of the all scalar metrics. We have the average quality per dataset and technique, which are on the marginals. We have parameter variance on the rightmost columns with the gray background. And we have a histogram of results as tiny bars inside each cell. The idea here is that if you have a cell with big bars on the left, it means that most of the runs for that particular technique, for that particular data set, had poor quality. And the converse is true. If you have large bars on the right, it means that most of the time the quality was good in that case. So what can we infer from this? Well, quality is very dataset dependent. We don't see a technique that is good for everything. So we have no clear winners in terms of techniques. But we have some clear losers like non-metric MDS and GDA, which you can notice by the dark green rows in the heat map. As for the projection-wise view, we have almost the same things. We have the aggregated quality, we have the average quality per dataset and technique, but we have a selected parameter preset instead of the parameter variance at the rightmost columns. Again, quality is very dataset dependent. Again, there is no clear winner, no clear best of all technique, but the same clear losers, unfortunately for them, I guess. Then we take one view and subtract it from the other to show how the presets perform when compared to the best results. And in most cases, surprisingly, presets are good enough, as you can see by the low error in most of the cells in this heat map. Okay, so putting all together, we try to answer many questions. Okay, unfortunately, we don't have time to present results for all those questions here, but you can find them in the full paper, of course. Then we did a projection of projections, sort of a meta-projection, to try to understand how the projections, how the results spread in sort of a quality space. So we took the 5 scalar metrics average for all data sets. So we have rows for each technique with 5 different variables for each one. Then we project them using MDS, which is a global distance preserving technique. And based on this, we select the best performing. So you can see that you have a sort of a quality horizontal axis and sort of a stress vertical axis. Okay, so by using this diagram, we could select the top performing ones for further analysis, which were UMAP, TSNE, PBC, and IDMAP. MDS itself almost made it, but we had limited space, so we had to cut it into 4 only. So, therefore, we did a study of selected top projections. As I said, UMAP, TSNE, PBC, and IDMAP consistently performed better, and we did some further testing on them to answer the following questions. How fast are the good projections, and how do projections spread their errors? Okay, so how fast are them? Clearly, UMAP and PBC scale much better. If you notice the red boxes, you can see that the time scale is pretty different between the 2 pairs of plots. And UMAP and IDMAP seem to scale very well with the number of dimensions. Okay, so this is an interesting result. And how do projections spread their errors? By using Shepherd diagrams, we can see that IDMAP seems to better preserve the distances. So you can see in the case of IDMAP for fashion MNIST, an almost perfect correlation, which is very good. Whereas for UMAP, you can see that it creates more distortions. So, as a summary of findings, best quality projections for these particular data sets, well, UMAP, TSNE, PBC, and IDMAP. Most projections perform well enough with preset configurations, which is not the case for TSNE, as you already knew. You still have to tune the perplexity to get the best results. Intrinsic with dimensionality, unsurprisingly, was the data attribute that was most negatively correlated with projection quality, but sparsity is the second one that correlates most negatively with quality. So you have to take care when using projections to reason about sparse data, which is an interesting result as well. Conclusions. Benchmarks are hard to construct. It's hard to find good implementations for every technique. It's hard to select good data, I mean sampling the trait space as we set out to do, and it's hard to select and find good metrics. But the payoff can be great in the end. Please refer to the full paper for more details and check out the companion site for code and data. And results, of course. That was it. Thanks for watching.
Thank you very much, Mateus, for the really nice talk, really clear talk. And Mateus, it's 6:30 in the morning for you right now.
Yeah, it's a bit early down here.
All right, great. Thank you very much for the very interesting talk, and it's really an amazing work you've done. You've done a lot. I mean, you've not only reviewed the data sets and the techniques like in rigor, but you've also implemented all these quality metrics. So it's really impressive work.
Thanks.
Lots of claps and lots of washing hand symbols coming from the YouTube channel. Right. So during the talk, Christian was just giving a talk, had a question. So I'll start with Christian's question. So his question was, when collecting data sets, how have you evaluated the intrinsic dimensionality of the data sets, and were they given? And I think I was also thinking the same, and even like put myself in the shoes of someone who's going to use sort of your approach, and how would one go about knowing the intrinsic dimensionality when you start with your own data set?
Yeah, that's a very good question. Well, when you are being that broad, I mean, evaluating so many things at a single time, we have to try to keep things simple, at most, and understandable for the end user that is probably part of the audience that we aimed this paper at. So we used a very simple but effective, in our opinion, technique, which is PCA. We used the intrinsic dimensionality is the ratio of principal components needed to explain 95% of variance in the data over the total number of dimensions. So if you need almost all of the dimensions to explain the variance of the data, we assume it has a very high intrinsic dimensionality, and the converse is true as well. I couldn't find at the time a better way to measure intrinsic dimensionality, and which was also simple enough to explain. We could, of course, use other techniques, but this one was the one that struck us as the most easily understandable from the user point of view. So, well,
so the good old PCA came to the rescue.
Yeah, as always. Why not? I mean,
yeah, maybe like information theoretic measures could be one way of sort of looking at the variation of sort of.
Yeah, you could have used entropy of the dimensions, something like that.
Some proxy measure, right?
Yeah.
Good. I'm sort of looking at the different channels. When people are sort of gathering their questions, I'll want to sort of maybe one question that's sort of a bit on the practical side, and that was part of it was, I think, in the previous question as well that we already discussed. So if you imagine a practitioner or a data scientist, let's say, who's going to refer to your survey to decide how would you, how they should start. Should they think of the data set first? Should they think of the sort of the techniques first? So what would be your recipe for using your survey results?
Oh, that's pretty hard to answer, but I think you can go either way. You can start from the top performing techniques. I think it's hard to miss by doing this. Okay, in the end, what we conclude is that techniques that preserve local structure in general perform better, such as TSNE, such as UMAP. So it's hard to go wrong with those, although you have the problem of tuning the hyperparameters like perplexity or number of neighbors in the case of UMAP. But this is one way to go. The other way to go, I guess, is to measure all those dataset traits and try to see how they fit in that dataset space in relation to the projection space, to the results. One interesting thing that we found out when doing this was that I had no idea. I think we all had no idea that sparsity played such an important role. Intrinsic dimensionality was kind of a given. Okay, so you have theorems showing that the higher the intrinsic dimensionality, the harder it should be to project data in a low dimensional space. But sparsity was kind of a surprise. So if you have like text data, which can be pretty sparse, you should take this into consideration. So what I'm trying to say is that as a recipe, as a general recipe, okay, start with those techniques, with local structure preserving techniques such as TSNE and UMAP. And if you don't have success, then measure the traits for your data set, and you have to compare that with the results and see what best suits you, more or less.
Yeah. I think that's a quite a good approach, right? So you start by looking at your data set characteristics. I mean, what type of data that I'm dealing with, and I think that then you have a much more informed decision what would be a good dimension reduction technique to apply. But of course, I guess sometimes finding or sort of finding out those traits might not be easy. So I've seen that you've shared a lot of material online. Do you have any sort of maybe helper tool or sort of a small script to that you sort of maybe like run your script on a data set and you get some notion of the data set traits? Have you done some tool like that?
No, we haven't, but it's a pretty good idea. In fact, what I'm thinking about is how to extend this work in a way that we can make the code more approachable, sort of creating a DR evaluation library. It's pretty far away from becoming reality so far, but if we get to do this in an easy to use way, so practitioners can use, not only researchers, this would be a great thing. And of course, you could do the data set trait evaluation built-in as well. The code to compute the data set traits is not that complicated, so it's quite simple to extract it from the code that we published and run that yourself. So that's a way too. Not that great as having a full-blown library to do this, but it's good enough, I guess.
Great. Yeah, I think it will be a good guidance tool. Okay, I don't see. I'll look one more time on the Discord channel. I don't see any further questions. So with this, I'd like to thank you very much, Mateus, for your presentation and for responding to the questions from all of us. And thank you.
All right. Thank you all.
So the next up in this session that we continue with again, a very interesting, very rigorous survey and evaluation paper called Quantitative Evaluation of Time-Dependent Multidimensional Projection Techniques. So this time from like the more conventional static projection techniques, we move on to the temporal time-dependent projection techniques, which are sort of quite interesting. So this is joint work by Eduardo Fassin-Vernier, Rafael Garcia, Jerome Prando da Silva, Joao Coma, and Alex Telia. So we can now move on to the presentation by Eduardo, and we'll be back with questions.
I'm here on behalf of my colleagues to talk to you about time-dependent multidimensional projections. Projection techniques take high-dimensional data and create a lower-dimensional representation whose visual patterns reflect some notions of similarity or structure in the original data. On the right we see two static 3D representations of the MNIST dataset, one generated by PCA and the other generated by TSNE. The scientific community has studied these methods at great length, creating dozens of techniques that optimize for different constraints, and categorizing, classifying, and testing these numerous methods. But most of these are not designed to deal with dynamic data, which may lead to misleading visualizations. Which one of these am I to believe? And how do I quantify how trustworthy they are? Our contributions with this work are: we've introduced metrics to quantify the stability of dynamic projections. This was something that did not exist in the literature before, and therefore we enable better study and comprehension of such methods. We created a benchmark with techniques, datasets, and metrics to study the performance of dynamic projection techniques. This benchmark is publicly available, and we hope it helps guiding future research on the topic. We introduce and test novel variations of existing static projection techniques under the context of time-dependent data. Let's start by describing the metrics we used. We used spatial and temporal metrics. For the spatial metrics, we have the neighborhood preservation metrics, which means basically that for each point we look at its neighbors in 2D and its neighbors in ND and see how well the sets match. For the distance preservation metric, we take the distances between points in ND and the distance between points in 2D and see how well these correlate. However, there are no temporal stability metrics in the literature. So we took distance preservation metrics and adapted them to, instead of looking at distances, now we look at movement. So we measure the stress and correlation of movements in the two spaces. As for the datasets, there is no readily available collection intended for this specific purpose. So we gathered and generated datasets from different sources, such as simulations, videos, and sports data. We were careful to try not to collect two datasets with the same characteristics or dynamics. And as you can see by the animation on the bottom of the screen, and by the features shown on the table, there is some variety to our collection. But the universe of possible time-dependent multi-dimensional datasets is huge. So all we could do was to try and do our best to get a sample that was simple and rough along these several axes. As for the techniques, we tested 9 of them, only one of which was explicitly designed to account for dynamic data. This technique is called DTSNE. DTSNE is a variation of TSNE, where stabilization term is added to the objective function, and the purpose of this is to reduce the amount of movement in the projection. And on the same paper, the author suggests strategies on how to organize the data and adapt static methods to generate dynamic projections. These techniques are time frame, which basically means run the projection algorithm independently for each time step and then stitch the outputs together. And global, which means concatenate all time steps of the input, run the projection algorithm once, and then separate the output back into the original time steps. These two strategies were applied to TSNE, UMAP, and PCA. The last technique we tested were autoencoder variations. We trained each autoencoder architecture to reconstruct the entire dataset over all time frames. Obviously, we couldn't cover all techniques and variations, but all the resources to expand the benchmark are available online, so you can run your favorite technique or experiment with new methods. Running all methods on all datasets and quantify inequality based on our metric set, we arrived at this aggregated view of the results. In this table, each row corresponds to a technique, and each column to a quality metric. Darker shades correspond to bad results, and lighter shades correspond to higher quality. At once, we start to see some patterns. For example, we see that timeframe TSNE and UMAP have good neighborhood preservation, while autoencoders and PCA are pretty good at preserving distances. These results are not unexpected due to the nature of the algorithms. In our study, though, we are especially interested in instability. Here we see that autoencoders and global PCA get the best results. To make things clearer, let's actually see these methods in action. In the projections, we see different patterns and clusters emerge from the visualizations, but the amount of movement seems similar between them. Here we also notice that DTSNE, the technique that was proposed to deal with dynamic data, didn't get the best results. Lastly, we can say that autoencoders and global PCA strike a good balance between visual quality and stability. All the resources used in this project are available at our online repository. Here you may find the description of the algorithms we use along with their implementations. So for example, if you want more details on the autoencoder we use for the Cartola dataset, you can open the notebook that has all the information about the architecture and training and see for yourself how we did it. All our datasets are also made available online, along with the code that generates them. So if you want to test your brand new dynamic projection technique, you may get the files here. You will also find the plots here in the paper, along with the raw outputs of the projection techniques. Videos and extra visualizations are also available. Finally, we value the replication of our work, so all the instructions to recreate it are available here. This work is an initial step towards understanding the behavior of dimensionality relation techniques in the context of temporal data. We hope that the information and results presented here help practitioners who want to understand their complex data, and that this work can be used by others interested in developing their own novel dimensionality reduction techniques. We proposed a publicly available benchmark with 9 methods, 10 datasets, and 12 quality metrics. To evaluate the viability of different techniques for the task, we computed spatial and temporal stability metrics for all possible combinations, thus providing an intensive collection of results. Based on the results, we presented a discussion that elaborates on the causes for understanding the dynamic behavior, and all our experiments are documented and detailed online. Also related to this work is the paper that is going to be presented at VisGap, where we discuss how to build benchmarks and talk about challenges of selecting and sharing dimensionality reduction techniques. Thank you for your interest.
Hi. Okay. Thank you, Eduardo, for this really interesting talk. Again, a very good work. And I'm passing on the claps over to you from the YouTube channel. And I'd like to start by saying that I think it's great that both in the previous paper and your paper, you make all this material available. I think it's really important that you're doing this, and it's really a great resource for the community to build on. So thanks again for doing that, being and supporting open science in general. So that's great. So I'm just looking at the channels. I don't see any questions yet, so I'll let everyone to think a little bit and sort of start with a question myself. I mean, just maybe following on from the previous presentation, from Mateus's presentation, where there was maybe a more emphasis on the data set criteria, selection the data sets, and then there we looked at static representations, not necessarily with the temporal dimension. But in your case, you looked at temporal data. Do you think we need different metrics? As far as I've seen, you have very similar metrics compared to the previous paper. Do you think we need to sort of look at new types of metrics for temporal data sets to sort of understand their traits better?
Yeah. We need to have these metrics to understand the projections and see how much of what we're seeing we can trust. But yet we have not a lot of measurements about the data sets themselves to measure the dynamics apart from the ones that we had seen on the previous work. So intrinsic dimensionality or sparsity or number of dimensions, these sort of measurements that are more related to static projections. But because we had so few of them, we only had 10 data sets, and there is no readily available collection of or benchmark that we can use. And most of these data sets, I had to go in and find a data source that I thought was interested and had temporal dynamics and sort of extract the data sets from that. So yeah, we don't have enough data sets yet to have these measurements and make them be very meaningful.
Mm.
But in the future, when we have more data sets and we expand on this work, yeah, it would be very interesting to have measurements to measure, for example, well, if points collapse or if they expand or if they change positions in the high dimensional space. But so far, we don't have it.
Yeah. I mean, maybe like some measures from the time series analysis literature might be of use, like periodicity or sort of seasonality of these temporal. I mean, if you treat them as almost like temporal, like time series, then maybe there are lots of new features that might be emerging.
Mm-hmm.
Right.
That's quite a good point. We hadn't thought about that, but definitely something to look for in the future.
That's great. Okay, the audience is a bit shy, so I'll continue with a few other questions. I think one thing I was thinking is, and I think that's a very unique characteristic of the temporal dataset, is the notion of stability, right? Because unlike the other ones where the stability is about the projection itself, I mean, here we have a stability in the data because this is temporally varying data. And I think that's one layer of very interesting complexity, because when you and this is common for all sort of time series type analysis, right? So you could either have methods that smoothen out sort of like spikes or jumps in the projection versus approaches that don't smooth out any of these variations that are sort of very sensitive and jump around a little bit. Do you think that instability might be a feature of the data that you might want to preserve in some of the projections? Is there a trade-off of like looking for stability? Maybe you're losing some of the important jumps that might mean something.
Mm-hmm. Yeah, I think it is important to portray instability, but the real instability in the data. And what you're trying to measure more in this work is seeing what are the artifacts that we may call it, because they are not part of the dynamic of the data, but just something that the algorithm did because it has a stochastic nature, or because the eigenvalues switch it and then a sudden jump happen in the projection that does not correspond to something that's happening in the data. And this is sort of what we're looking for. And once we have a more stable projection, then we don't have this misleading movement, and then every movement that happens we can trust, and then we can really see when there's instability in the data itself, because we can trust what we see.
Yeah. I think that's what makes this problem really interesting, because of all these layers of complexity. Like looking for other questions. Then maybe one final one, and it's a very similar question that I asked to Mateus as well. Like then you mentioned maybe this could be a guide for practitioners to make some informed decisions when they're choosing a projection technique. So what would be your recipe for a practitioner to use your survey to choose a good applied technique?
I think, like in Mateus' work, we find out that there are some techniques that maybe there are no clear winners, but there are some clear losers. So we might steer away from them, and the ones that are closer to being winners at this point are our global PCA approach and the autoencoders methods. Those we had a lot of success. So if you want to project dynamic data, we would recommend to stick with those. But now we have laid down all the infrastructure needed to develop new techniques. So we're already thinking about, well, can we take a DTSNE or UMAP approach and somehow make it more stable to better understand data. So for now, if you're a practitioner, I would stick with those techniques that I mentioned before. But if you're a researcher, I think there's a lot of space to explore, and there are a lot of ideas that might work in this context of dynamic data.
Great. Thank you.
Thank you.
There's a comment from Helvig that it's sort of and praising that it's very good to have all these study results and information available, so that readers and users can bring their own experience and own expertise to decide for themselves. So I think with this, I'd like to close. Like to move to the next presentation, because I don't see any other questions on the YouTube channel either. So thank you very much, Eduardo, for your really interesting talk, really good work.
Thank you.
And for responding to all the questions quite nicely. So thank you. So next up, we have one of the best paper candidates for this year. So we are looking forward to a very interesting talk now. It's called The Phase-Space Projection of Dynamical Systems from Nemanja Bartolovic, Markus Gross, Tobias Günther from ETH Zurich, and the work will be presented by Nemanja. So we'll listen to the talk now, and then we'll be back with questions in about 10 minutes.
And welcome to the presentation of our paper titled Phase-Space Projection of Dynamical Systems. My name is Nemanja Bartolovic, and I'm a PhD student at ETH Zurich. Today, I'd like to talk about the visualization of motion. To illustrate the problem, let us start with the motion of a pendulum. The motion of a pendulum is determined by two numbers, the angle and the change of the angle. A simple ODE describes how these two numbers evolve. If we plot the two numbers in 2D over time, we see that the pendulum traces out a trajectory. This 2D space is called the phase space of the dynamical system, and it contains all possible trajectories a pendulum can take. As another example, consider the circular restricted three-body problem, where an object, such as an asteroid or a spacecraft, moves according to the acceleration field of two celestial bodies, such as Earth and Moon. When restricting the motion to a plane, The object has 4 state variables, 2 for position, x and y, and 2 for velocity, u and v. This means that the phase space is 4-dimensional. How do we visualize its trajectories? Or more general, how do we visualize trajectories of any dynamical system with even more dimensions? To answer this question, we developed a dimensionality reduction technique aimed at trajectories in the phase space of dynamical systems. Before proceeding onto the method description, it is worth exploring some of the related work on the topic of multidimensional data visualization. There has been a plethora of dimensionality reduction techniques developed throughout the decades with different strengths and limitations. We would particularly like to mention TSNE and UMAP, which have seen widespread use in different types of datasets since their invention. However, when we apply UMAP, for instance, onto high-dimensional curve data, we could obtain the result as shown on the right. The problem is that there is no strict connectivity constraint embedded in the algorithm, as it was designed to tackle generic high-dimensional point datasets after all. Even though the input curve is completely connected, the projection appears disjointed in several locations, as visualized by the red arrows. This is one of the problems that we aim to rectify. Beside the dimensionality reduction methods, it is worth mentioning interesting work in high-dimensional flow visualization. Hoffman et al. Developed a 4D camera projection technique that enables exploration of 4D vector field topology. With our method, we do not have a restriction on the dimensionality of the input data. Now we will describe the details of our method. The goal that we stated to accomplish was to project high-dimensional curves from a phase space down to 3 dimensions, ready for visualization. These high-dimensional curves, illustrated as dark gray in the image, are represented as sets of sample points, where each point has an associated position and velocity. In order for the projection to remain continuous and smooth, we define the projection operator as a non-invertible differentiable map P. With this definition, the velocity of the output low-dimensional curve, shown in green, is transformed by the corresponding Jacobian. The question remains, how do we constrain this map? Ideally, we would like to constrain it in a way that preserves some of the geometric properties from the high-dimensional space, such as the curvature of trajectories or the tangent magnitude. Intuitively, the goal is to replicate the behavior of the high-dimensional flow such that the faster-moving regions in the original data are represented by similarly fast-moving projections in the low-dimensional space. In order to support multiple trajectories in a single dataset, we also constrain the projection map with distances to neighboring curves. By considering neighbors, the spatial organization of the projected curves is significantly improved. Optionally, we can specify critical point projections. Critical points are equilibrium points in the phase space that have zero velocity. This constraint helps to pin down the whole projection around a specific location in the low-dimensional space. In order to resolve all of the aforementioned constraints, we parameterize our differential map P as an n by m polynomial map. Thereby, each row of the map represents one output dimension and is computed by an independent polynomial of up to d degrees, where d is user specified. Given this definition, the problem boils down to determining the unknown polynomial coefficients that comprise the map. An example of such a map is given here, where we wish to compute a 3-dimensional output and expect 4-dimensional curves as input, with the polynomial degree set to 2. To find these unknown polynomial coefficients, we set up an energy minimization problem where we convert all of the desired properties into constraints. These constraints include curvature, tangent magnitude, neighborhood distances, and optionally the critical point projections. In addition, all of these constraints can be weighed individually in order to achieve the desired projection. The different weights are particularly useful if the orders of magnitude of different constraints differ a lot. Finally, we use a nonlinear least square solver to optimize for the projection parameters. In the following slides, we will showcase some of our results. In order to do so, we have applied our method to several dynamical systems. One such system is a circular restricted 3-body problem which can be described in a 4-dimensional phase space. Next, we have a damped double pendulum system where the equations of motion are observed in angles and changes of these angles. This configuration also lives in a 4-dimensional phase space, where the state consists of the 2 angles and their changes. Last but not the least, we will also present a few examples with simulations of inertial particles in fluid flows. In such a system, we observe particles of a certain mass and starting velocity as they get advected by the 2D flow. If this flow is also time dependent, the state dimensionality is increased from 4 to 5 to account for the time variable. As the first motivating result, we show a projection of a single trajectory of the CRTBP dynamical system. The motion of the particle can be observed by the red highlight, and we can see that its movement is continuous and consistent both in the visualized subspaces of the phase space and the final 3D projection. There are no sudden jumps or discontinuities in motion, and the projection also exhibits symmetric patterns. Next, we compare our results to other dimensionality reduction techniques. With principal component analysis, the projection is largely dominated by the increased values of the velocity subspace, hence the disk-like appearance. Both TSNE and UMAP produce interesting visualizations, but sometimes have unexpected discontinuities along the curve. Our method is shown for comparison. One of the metrics that we use to assess the utility of our results is the stability with different integration durations. We run 3 simulations of different time durations and project them independently. As a result, we obtain very similar looking projections that differ only by the length of the input curve. Compared to our projection, other methods tend to produce very different results, even though the underlying phase space manifold remains the same. In addition, we can notice an emergent structure with the UMAP projection, but that unfortunately requires a lot of samples which may not always be feasible. Next, we show results for the double pendulum system. The initial configuration consists of 4 different trajectories, each starting from the same position, but due to varying starting velocities, end up in different final rest states. When using our method with just the geometric constraints to project these trajectories, we obtain the result in the middle. We can notice that the resulting projections are fairly interwoven and difficult to discern. After enabling neighboring constraints, the new projection map spaces out the curves according to the corresponding distances, and the resulting projections become easier to see. In the following configuration, we once again have 4 trajectories of the double pendulum system, but set up in such a way that 2 of them end up in one critical point and the other 2 in another. Our map preserves this assumption from the high-dimensional space by projecting them around their final critical points. In contrast, TSNE and UMAP attempt to separate all the trajectories as individual, distant entities and inadvertently break their connection to the associated critical points. Another interesting result is the explicit representation of our projection map. Given this formulation, we can apply an optimized map to new, similar data compared to the dataset that we have optimized the map with. As an example, we show inertial particle motion in a forced Duffing equation phase space. We jointly optimize 3 different trajectories, yellow, purple, and orange, and visualize corresponding critical points as spheres. Next, we repeat the optimization process, but include only the yellow and purple trajectories. Finally, by just using the projection map from the middle illustration, we explicitly project the orange trajectory without optimization. As a result, the orange projection appears in a similar way as if it was jointly optimized with the other trajectories. This is possible due to the smooth and continuous definition of the projection map. The results that we have shown so far have been derived from 4-dimensional curves. The first higher dimensional scenario shown here is given by the inertial particles in a time-dependent flow, where the input curves are specified in a 5-dimensional space. The 6-dimensional example is obtained by projecting a curve from the CRTBP system, but configured in a way that allows for motion in the z-axis, effectively increasing the subspaces of position and velocity to 3 dimensions each. Another important aspect of the optimization are the weights. We have mentioned that they are useful in order to balance different constraints accordingly. For the following images, we assume a single trajectory simulated in the 3-body system. First, we show a projection that is obtained when we project this trajectory using only the curvature cost. The colors on the 3D visualization match up well in the upper part where input and output curvature is visualized, but differ for tangent magnitude in several places. Next, we have the same setup, but optimized only for the tangent magnitudes. In this case, there is a large difference in the curvature of the input and output curves. On the other hand, the tangent magnitude matches perfectly. Finally, we enable both of these constraints and perform the optimization. We can see that both costs are now matched up well. In addition, in a variety of cases, this cost configuration tends to give the best visual clarity of the projection. In the following video, we show how the optimization proceeds in real time for a single trajectory that consists of 5,000 points. Since the optimization is iterative, its intermediate steps can be visualized and can be interrupted at any time. Finally, we would like to list some of the limitations that we have identified with our method. The objective function is not strictly convex, which may lead to different local minima. While computational cost was acceptable for the majority of datasets we have used, the scalability and performance issues arise with higher input dimensions and larger datasets. In addition, the projection map is not invertible, which could lead to different points being mapped to the same location in the projection. This problem is generally mitigated with the usage of neighborhood constraints. In summary, we formalize the projection of a high-dimensional vector field and describe its local and integrated flow properties. We formulate the projection as a tensor product and optimize the projection for varying polynomial degrees. In the future, we would like to explore different optimization schemes that could be used to optimize the projection map, as well as work with higher dimensional data and improve overall scalability and performance. Thank you for your attention.
Thank you, Nemanja, for this really, really nice talk.
Thank you.
Very nicely explained as well. And again, as previous talks, I'm extending the claps and applause from the audience over to you. And yes, I'm sort of watching for some questions. There's a question on the Discord channel from Helvik Hauser. And his question is, when considering phase space images of the trajectories that you've shown, the individual semantics of the axis can be quite important for interpretation. And the question is, does this become difficult after projection?
Yes, that's true. Yeah. That's true. I mean, in the output space, we don't really know what each dimension actually represents. It's just a visualization to help you reason about a shape, or perhaps proximity to some other critical point, or how the particular trajectory would look in relation to another curve or another trajectory, and so on. Those are, I guess, the best takeaways from the method. And not so much about interpreting individual axes.
Okay, and I was thinking, I think in that sort of part of it is also in your response. I was also wondering whether some of the structures that we see in your projection are sort of meaningful or sort of could be interpreted in ways. I mean, some of these spirals or areas where the curvature in your projection changes dramatically, or where there is some sort of I don't know, maybe there are like two areas where there are two different spirals and then they're connected in between. Have you looked into the interpretation of any of the resulting artifacts or sort of some structures that might be visible in your projections?
Well, for the particular case of CRTVP, the three-body problem, in that case we were mostly looking to see whether we would preserve the similarities and the other high-dimensional features down into the low dimension. As for the spirals, I mean, the movement is a bit more involved. It's not just a spiral; it's more of it's like a star-based movement. It just has many different endpoints, I guess. It's basically the Earth is supposed to be in the middle, and then the Moon is somewhere else on the side, which is not visible on the phase space subspace.
Great. A fun question from Philip Sadler on the YouTube channel. Philip asks, can, for example, intersections persist, and could the user see that? And then the question, since the constraints are not hard.
Yes, that's certainly possible, unfortunately, because the map itself is not invertible and it could map multiple points into the same position. Luckily, I mean, for the first optimization, this should not happen in theory, because in practice, because the points themselves are separated by the neighborhood constraints if we use those. And if we don't use those, typically that's a scenario where we only have one trajectory. In such a case, we have the continuity constraints, for example, for the curvature and tangents, which will prevent such self-intersections, hopefully.
Okay.
After projecting a new trajectory, if you already use an established projection operator, which was already optimized because it's an explicit one. You can also use it to optimize any other curve that you'd like if you use it on the data sets from the same dynamical system. If they're close enough to the original data sets, you could use it and you will get something perhaps meaningful. But if you try to use it on something that's super far away from the data sets that you're trying to optimize for, then you might get something weird. I mean, the output could be very, very different.
Okay, thank you, Nemanja. I think that was a clear response. Okay, one more question on the YouTube channel from Christian. How different, and his question is, how different are the local minima you obtained when running the algorithm multiple times?
That's a good question, yeah.
Are they similar? I mean, just to sort of like, he also sort of elaborates a little bit, are they similar to a certain degree or completely different? Or are there areas that are stable or that are unstable? So have you observed any of these in your simulations?
Yeah, so in our paper, we have actually included a small example with the 3 different local minima that we would get using the same starting conditions and same parameters for the problem, because in the end, the map is initialized randomly at the beginning and then optimized for. However, this could certainly be improved in the future. And as for the stability, we used to test this using subsampling techniques, where we would, for example, subsample the curve such that we would remove every second point and redo the projection again and see if we would get the same results. This is not something that we include in this particular video, but it's again in the paper. And we also use the stability technique where we would cut off the curve, for example, simply simulating it for a certain amount of time, so the integration would reduce or increase. And we would again try to match the same shape. And overall, it depends on particular starting initial conditions, as with also with other algorithms. But with ours, typically we selected the solutions that appear the most frequently, right, for very different random initial conditions. So we didn't select just the one that's maybe the best because it looks the best, but rather the one that actually appears the most often. So I guess under different stability tests and conditions. I guess that was the main goal. So I would say that the projection with the Bishal, for example, for CRTVP with a kind of a toral shape, that's the one that appears across all different stability tests, and we believe that one represents the results in the most optimal way that satisfies the constraints that we have imposed.
Yeah, great. Thank you very much. Just looking at another question from the YouTube channel from Douglas de Oliveira. He first of all thanks for the nice work and presentation. And the question is the dimensions of the phase space inherently low, like less than 10 dimensions?
Yeah, that's true. We have mostly tested in the data sets which would have 4, 5, or 6 dimensions. The reason being that, of course, as you increase the dimensionality of the input, the computational costs also rise. And this is something that we will look to improve in the future. Ultimately, we would also like to be able to use something like this on a much higher dimensional data set where it will perhaps provide even more insight into how these things evolve and how the systems work.
Maybe like if thinking about the earlier paper in this session, I think this would be a big improvement to the established techniques, because none of these techniques care about continuity, whereas you sort of
exactly, that was one of the primary goals that we would have wanted to constrain our projection with, to have something that's continuous in a way.
Yeah, I think that's the really the unique and really strong contribution of your technique, is to be able to do that compared to what was out there previously. Great. Another question from Renata Raidu on the YouTube channel, and her question is: she says sometimes it's important to localize the behaviors in the trajectories. For example, fast changing areas with respect to sort of maybe subsets of dimensions. And her question is it possible to sort of get a sense of these localized behaviors in the trajectories? Is that possible?
It depends, I guess, on the initial conditions and the data set, but what we noticed in our results is that this typically happens in the projection. It's not something that we have unfortunately visualized in the video, but for example, again, for that toral shape for the CRTVP problem, the inner part of the ring are the points which have high velocity, and the outer part, the shell sort of, is the one that has the slow moving parts. After we visualize the heat map of velocities, that's how it looks like. Certainly we wanted to preserve these regions, particularly because of the tangent constraint that we added. That's something that helps us actually preserve the slow parts and make sure that they're slow in the projection, and also the high parts to make sure that they're the high velocity parts to make sure that they're also fast in the projection space.
And it was a bit fast, but I think in that slide that you visualized on the motion, curvature, like towards the end, the weights or the preservation of the magnitude and the curvature, you somehow managed to sort of visualize those parameters, right?
Exactly. There we have visualized the input and output velocities or curvatures on the projection itself, so it's actually possible to see the points in the heat map, and you will see that as long as they match, the constraints are satisfied. If the colors are off between the two different values, like the input and output values, then you would notice that it's the constraint was not satisfied. So in a way, you would notice that if the velocity numbers are the same, so yellow parts are high velocity, purple parts are low velocity with the Viridis data color map, then the constraints actually work towards creating a projection that keeps the slow parts in the projection as well as the fast parts. So in a way, it works.
Yeah, and just a comment and a question from Helvig on the Discord channel. So he's saying, I wonder to what extent, to what degree, such a projection may help with spotting interesting topological features in multidimensional dynamical systems. Would you like to respond to that?
Sure. I guess something based on a method like this, or some sort of application would be, I guess, to do something like trajectory planning, perhaps. Of course, it would require a bit more of an elaborate process for that, but we can also, for example, notice maybe we can identify symmetries or how close certain trajectories are to critical points, because critical points will also naturally map to zero velocity points in the output space because of the way that the projection operator is defined. So certainly there are areas where we could explore the application of the method, and this is something that we would like to do in the future for sure.
Thank you very much, Nevanja, for responding to the questions in great detail, and thank you again for the really interesting talk, and also being a best paper candidate. So that's really good work. And with this, we have reached the end of this really interesting, really rich session. So thanks to everyone for being on the channels and asking your questions. And I think we are now moving into lunchtime. It's a bit early for me for lunch, but so enjoy your lunch, dinner, coffee, depending on your time zone, and hope to see you around in the next round. Take care. Bye.